Hello, welcome to our first video lecture for advanced physics. What you see on the screen right now are the quantities that we defined last class, where last class we talked about linear position, linear velocity, and linear acceleration, and we saw the analogies between rotational or angular position measured in radians, angular velocity measured in radians per second, and angular acceleration measured in radians per second squared. Today, what we're going to focus on is how these two sets of quantities can be related to one another. To show you this, I'm going to pull up a video of a rotating disk. It's going to be really, really exciting. Alright, so here we have a turntable, and we're going to focus on this pink sticky note on the turntable as the turntable spins. I told you, exciting. And there it goes. So as this rotates around, we know that this pink dot is going to travel some linear distance as it goes around, and it will also cover some angular distance. But how are those things related? That is the question that we're going to answer. All right, so I've imported an image of our rotating disk, and there are a couple quantities that we first should define. So I'll take a look at this image here. We have the center of the circle, right? And we know that from the center of the circle to the pink dot, there is some radius that we call r. Okay, so at the time that's shown, then we have that as your distance r. We also know that there is a linear distance that this pink dot has traveled through. Here was a starting point, and we can see all the little dots, and the linear distance that it travels is just the distance along the circumference, and we call this S, and that should be familiar as an arc length from your math class. We can also define an angular distance that this pink dot has traveled through, and that is given by theta. Okay. So then the relationship between these should look somewhat familiar, and that is the arc length is equal to the radius times the angle theta. Now, if I want to talk about how fast this object is traveling, then I can talk about the linear velocity, which is a change in s over a change in time. Doing that to both sides, I get a delta r times theta over a delta t. Now, the radius doesn't change with time, so I can pull that out, and all I really care about is a change in angle over a change in time. And again, on the left-hand side, a change in linear position over a change in time is just the linear velocity. So there we have it. The linear velocity is equal to r, and this delta theta over delta t, well, that's the angular velocity. So that's how we can relate linear velocity with angular velocity. Just like we can relate linear position with angular position through the arc length equation. Now we can do the same thing and get a relationship between the linear acceleration and the angular acceleration. All we have to do is take a change in velocity over a change in time. Again, the radius remains constant, so that's going to get pulled out, and this is going to be a change in angular velocity over a change in time. So on the left-hand side, we have a linear acceleration is equal to r times the angular acceleration, alpha. And there we go. We have three equations now. The arc length equation, an equivalent for the velocity equation, an equivalent for the acceleration equation that relates linear quantities to those angular quantities. Okay? So that was the number one goal of this lesson. Now, there's a subtlety in what this linear acceleration is. And if we go back to our picture here, then we know that an object traveling in uniform circular motion is going to have what we call a centripetal acceleration directed towards the center of the circle. That's your centripetal acceleration. We also know that the velocity of this point is traveling tangent to the path, tangent to the circle, and this is your linear velocity. we know that this centripetal acceleration exists whenever an object travels at constant speed. But what if this turntable were speeding up? What we do know is that if an object speeds up, then there must be an acceleration in the direction of the velocity, and that will give you a speeding up or slowing down. This we call a tangential acceleration. So if an object's going to rotate at a faster and faster rate, there's an angular acceleration, and it's this angular acceleration that's related to this linear acceleration that's tangent to the path. The centripetal acceleration has nothing to do with an angular acceleration. So if we wanted to be more complete or more thorough, what we would write is that this acceleration is the tangential acceleration, and it's related to the angular acceleration by this equation, at is equal to r times alpha. And just to remind everyone, we know that the centripetal acceleration is equal to v squared, the linear speed, divided by the radius. These two quantities are completely different. They are at 90 degrees to one another. The centripetal acceleration exists when there's constant speed. The tangential acceleration only exists when our object is speeding up or slowing down as it travels in a circle. The total acceleration is going to be given by the vector sum of the centripetal acceleration squared plus the tangential acceleration squared. Now, the last thing we have to cover are the kinematic equations. We know the kinematic equations in linear motion. Magic. So now we can write the same types of equations for angular motion. And all we have to do is replace the linear quantities with the analogous angular quantities. So our linear position becomes a theta, so it's theta is equal to theta 0, initial position, plus initial velocity times time, plus 1/2 angular acceleration times time squared. So you see how all we did was replace the linear quantities with the angular quantities. All right, so the second equation would become angular velocity is equal to omega 0 plus alpha times time. And the third equation would be omega squared is equal to omega 0 squared plus 2 alpha times delta theta. These three equations for angular motion are not different than the three equations we had for linear motion. And don't think of them as different equations. All you have to do is take the three kinematic equations, which you guys know so well, and replace all of those linear quantities with angular quantities. And again, remember that these three kinematic equations will work for any problem as long as acceleration is constant. And the same holds true for angular motion. The angular acceleration needs to be constant in order for you guys to apply these three equations in your problem solving. Good luck on the homework. Alright, so let's do an example problem using these three kinematic equations. And I will be doing example 10-1 from your textbook. Example 10-1 in your textbook is called Thrown for a Curve. How clever. It's an example about a pitcher who throws a curveball, giving the ball an initial angular speed of 36.0 radians per second. When the catcher catches the ball, has a final angular speed. Sorry, my rice is done cooking. That's what that noise is in the background. There's a final angular speed of 34.2 radians per second. And the time it takes for the pitcher to throw the ball is 0.595 seconds. All right, so what they want you to calculate is first find the angular acceleration. The second thing they want you to do is determine how many revolutions does the ball make before being caught? Question mark. All right. So, how do we go about solving this? In order to get the angular acceleration, we first identify that we want the quantity alpha. We're given an initial omega, and we're given a final omega. We're also given the time. So, we know we have one of the kinematic equations which says omega is equal to omega 0 plus alpha times t. So here, all we have to do is plug in values for omega f, which is 34.2 is equal to 36.0 plus alpha, which we don't know, times time is 0.595 seconds. Rearranging the equations, we can solve for alpha, which is going to be equal to negative 3.03 radians per second squared. Now, whenever you get an answer, especially when there's a negative, we should think what this negative means. This negative means that it's in the opposite direction as what we consider to be positive omega. Okay? So omega was positive to begin with, it's positive to end with, and acceleration is negative, which means that the ball is slowing down. And indeed, we see that it starts with an initial angular velocity of 36 radians per second, and it ends with a final angular velocity of 34. So it has slowed down. So it's good that our angular acceleration is negative. I also know my answer is right because I'm looking right at the example in the textbook. All right, so how many revolutions does the ball make before it's getting caught? So if you want to know how many revolutions, we want to know this theta, or delta theta rather. Okay, so we know initial angular velocity, we know final angular velocity, we know time, and now we know alpha. So we can use the kinematic equation, the first one, and delta theta is equal to omega 0 times t plus 1/2 alpha times t squared. We know initial velocity, we know the time, we know the acceleration now, so we can plug in all those values, and if you do that, you should get an answer of 20.9, and since we are using all of the proper SI units, this is 20.9 radians. Now they want to know how many revolutions this makes, so you have to multiply by the conversion 1 revolution per 2 pi radians. Now our radians will cancel out, and we have units of revolutions left over, and the final number you should get is 3.33 revolutions. Good luck with your homework.